Hello all, welcome to the new video of Signals and Systems. In this video, we'll study about transmission line equations. So before going further, we'll recap what we had studied in the previous video. So in the previous video, we had studied about transit time effect. So what it stated was the signal which is v of t cannot travel to load with an infinite speed. Okay, even it will have finite speed. So it takes, if the length of the transmission line is L and the velocity of the signal is v, then the transit time is defined as Tr is equal to L over v. Okay, because of this time, because of the transit time effect, the voltage which is at A dash, say VQ, will not appear instantaneously at VB dash. It will appear, this VQ will appear at B dash only after some time, that is called as transit time. Okay. So when the voltage across A dash was VQ and it was transmitting it, the voltage at B dash was VT. Only after TR seconds, voltage at B dash will be VQ at B dash. However, at that time the voltage at A dash would have been different. It is VQ, it will become VR till the time this VQ will reach the B dash. So this is what is called as transit time effect. Okay, we had studied this in detail in the previous video. And coming to the transmission line, so at low frequencies we can ignore this transit time effect. Okay, at that time we can model this whole transmission line as, say, one resistor or one capacitor or whichever. However, at higher frequency we cannot ignore this transit time effect. I will just show you an example. So we studied about transit time effect in detail in the previous video, and I also did a short recap in this video. So many students will be having this question: does it really matters when the signal reaches its load? Because many of you will ask me, in our first sem or second sem class, in the basic electronics class, we didn't care when the signal reached its load. If our teacher had asked what is the output voltage here, we had said VO is equal to VI. We didn't say VO is equal to VI. Let's say this is 3 meter. Then the students didn't say the VO is equal to VI after 3 meter upon 3 into 10 raised to 8 meter per seconds. Okay, this is the velocity of the signal. This will be 10 raised to minus 8 seconds. So nobody answered that the voltage at the load will be equal to 5 volts after 10 raised to minus 8 seconds, because at that time we used to deal with low frequency signals. Remember this. In our previous classes, in the beginning courses, all we had dealt was low frequency signals. We didn't go beyond megahertz or gigahertz signals, because the circuit behavior will change drastically if you move to high frequencies. Okay, so that's when the effect of transit time will come into the picture. Hence the name transit time effect. We have to consider it if we want to analyze the circuit properly at higher frequencies, because VO will not be exactly equal to VI in this case because of this large frequencies. Okay, remember this. And also many of you might have done the lab, okay, analog electronics lab. In that, nobody bothered how much is the length of the wire which is connecting from load to the source. Did we bother analyzing the wire? No. However, at larger frequencies, even the length of the wire can have more impact on the output. Okay, because the transit time effect will be appreciable, because Just see, in this case, the frequency of the signal is 100 Hertz, which means the time period is 0.05 seconds, whereas the transit time TR is 10 raised to minus 8 seconds. So in this case, TR is much lesser than time period T, which is important. Okay, when this is the condition, then you can ignore it. The output will be equal to input. You do not bother about transit time because it is much lesser than time period of the signal. However, at 1 megahertz, my time period will be 10 raised to minus 6 seconds. This is 1 microseconds, and the transit time will be 10 raised to minus 8. So it is very close to 1 micro. When you compare this and this, in the second case, TR is almost equal to time period. So the transit time has its effect on the circuit behavior. Okay, so it's because of this reason we have to study a separate topic called as transmission lines. Transmission lines is nothing but a wire connecting the source and load in a simple term. Okay, so that's why we have to mathematically model this transmission line. Then only we can see how to optimize the circuit behavior. How we can get VO is exactly equal to VI even at high frequencies. You'll understand that after modeling this transmission line, that is two conductor system, which we had studied in the while studying transit time effect. Okay, so whenever someone asks you why to study transmission line, you tell them because boss, at higher frequencies the circuit behavior will not be as you predicted, because the transit time, that is the signal speed, will also will determine the circuit performance. Okay, so that's why it is important to study the transmission line. An entire topic textbook is dedicated to study this transmission line. This is the nothing but a transmission line. Okay, so let's see that how to mathematically model a transmission line, then we can appreciate it. Thank you. So before we go to the actual transmission lines equations, we need to understand how to model transmission lines. Okay, as you can see here in the case B, there is a voltage source V of t, and its input frequency is of 100 Hertz, and we have connected a load. So as we know, at lower frequencies the transit time can be ignored. Okay, so the circuit behaves as we always know. Okay, that is in a basic electronics class we understood that the output voltage is nothing but the input voltage, that is this 100 Hertz output. So the transit time is very negligible and it can be ignored. So when I say I want to model this circuit, I essentially mean that this wire which is connected from source to load has some resistance. Even if it is negligible, it has some resistance. Okay, say 1 ohm. So that 1 ohm I have represented using this resistor here, that is the resistance of the wire. Then we have the signal V of t, and then there is a load. So what I did just now is called as modeling of this actual circuit. Okay, so this type of modeling is called as lumped circuit analysis. Okay, by mean lumped circuit model, I mean that the entire wire, its resistance drops from here to here, but what I did, I combined all this resistance into single resistance, or it is concentrated at the center, and on the either side it is connected by a perfectly conducting wire. Okay, so this type of modeling is called as lumped circuit model. So whenever we have to understand the system, we need to convert it into a lumped circuit, then only we can understand what's going on. Okay, so actual word is very complicated. In order to understand that, we need to make it simple. Then only we can understand it, we can model it using equations and all that. Okay, so this modeling is not simple in this case, that is case A, because in this case the transit time TR, which is L over V, is approximately equal to the time period T of the input signal. Okay, so I cannot essentially model this system, that is this transmission line, into a single resistance like I did here. Okay, so in transmission lines the circuit elements R, C, L and G, that is resistance, capacitance, inductance, all are not concentrated at a single point like this. Okay, they are distributed throughout the transmission line. It is distributed throughout the transmission line. So in order to understand this system, we need to first convert it into lumped circuit. Because the circuit elements are distributed, we need to divide this transmission lines into different subsections, that is smaller subsections. Then only we can model the transmission line as a lumped circuit model, then we can understand it. Okay, so since the transit time is approximately equal to T, we cannot model whole system as a single entity. So we need to divide this transmission line into different subsections. So we need to divide these transmission lines into different subsections such that over the small subsection the transit time is negligible. Because remember that the rule here is lumped circuit analysis is valid provided the transit time is much lesser than T. Okay, so we are interested in doing lumped circuit analysis. So we need to make sure that in a circuit where we are analyzing, the transit time is much lesser than time period of the signal. Since the whole transmission line, in the whole transmission line, the TR is approximately equal to T, this condition will not get satisfied. So we are dividing this transmission line into different subsections where TR is negligible. Even if we divide it into different subsections, okay, remember listen this carefully. Even if we divide the transmission line into smaller subsections, even in this area, the after certain frequency the transit time will be approximately equal to T. So our lumped circuit analysis will not be valid even after certain frequencies for even this small subsection. Okay, but however, so there our condition fails, so we cannot do lumped circuit analysis, and whatever analysis we do, it will not give us the correct result. So in that case we have to use the limiting factor, that is we have to use limits. Okay, limits means I have to use limits where subsection tends to 0. This I have to use so that the lumped circuit analysis will be valid at all frequencies for a transmission line. So what we are to summarize this, what we are doing here is we are dividing the entire transmission line into smaller subsections, and these smaller subsections are modeled like this as a single resistor or capacitor or inductance based on the different elements. Okay, so with this keeping this in mind, we'll see the mathematical equations. Okay, then you can appreciate what I am telling. Okay, so please, this is a little complicated, just sit back and understand what's going on very slowly. Okay, so let's see the actual transmission line equations now. So as I told earlier, in order to carry the lumped circuit analysis, the transit time effect should be very much less. That is, the transit time effect should be so less that it can be ignored, like how we did in the case of low frequency signals. Okay, so since in a transmission line of say of certain distance x, we cannot ignore the transit time effect. It will have its own effect on the circuit performance. So we need to consider transit time effect. However, if we want to model a transmission line, we cannot do so for a whole transmission line because of that transit time effect. So what we do, we divide the transmission line into different small subsections, where in that small subsection the transit time effect can be ignored. So let's consider a small section of a transmission line of length delta x. Okay, so in that case the two conductor system which we saw earlier can be represented by four characteristic circuit parameters. Okay, so they are resistance, inductance, shunt capacitance and shunt conductance. As you can see here, these are the four parameters. So the equivalent lumped circuit for the infinitesimal section of the transmission line can be shown as shown in this figure. Okay, so this is the voltage and current on infinitesimal section of a transmission line. So let the voltage at A dash be V. So this will induce some current I. So the voltage at B dash will be say V plus delta V, and the current will be I plus delta I. Okay, so what we are doing here, we are applying a sinusoidal voltage of angular frequency omega at A dash, and it will generate some current I which will flow into the terminal A. Now due to the voltage drop in the series elements, that is resistance and inductance, okay, the voltage at B dash will not be same as A dash. Okay, at A dash the voltage is V, so at B dash the voltage will be V plus, say V plus delta V. Okay, in the same manner, some part of the input current will be bypassed through this conductance and this capacitor. So current at B dash will not be same as at A dash. So let the current at B dash be I plus delta I. So this is the assumption we make. Okay, so if we assume these things, then we can write delta V as minus of R time delta x plus j omega into L delta x into I. Okay, that is voltage drop across these two elements. Note that the signal which we are applying V, let's say V of t is of omega radians per second. Okay, this is the omega which we are using here, and then the current I will be delta I will be minus of g times delta x plus j omega c into delta x times v. Okay, these are the two circuits, two equations for delta v and delta x. Note that the negative sign indicates that the voltage and current at B dash are less than that of A dash. Okay, so that is what this represents. So next we will simplify this equation now. So we will further simplify the equation. So that will become delta V by delta x, that is we will take the x common, minus R plus j omega L times I, and then delta I upon delta x will be minus of g plus j omega c times v. So what we have done, we divided this entire transmission line into small subsections, and for this small subsection we are modeling in terms of these equations. Okay. However, after certain time, after certain frequency, even in this small subsection, the transit time effect cannot be ignored. Okay. So in that case, for our analysis, that is what we are doing here. This is what we are analyzing. This is called lump analysis. In order for this to be valid at all frequencies, this delta x, that is the length of the small subsection of a transmission line, should tend to 0. Okay. If it tends to 0, then what happens? Then there will be no transit time effect. Then we can carry out the analysis, which will be pretty accurate. Okay. So next, we'll make this equation valid for all frequencies. So in order to do that, we'll do a limit delta x tends to 0, delta v upon delta x, which is nothing but dv by dx from the definition of derivation. This will be minus r plus j omega l into I. In the same way, limit of delta x tends to 0, delta I upon delta x will be di upon dx. This will be minus of g plus j omega c times v. Okay. So we found out that the voltage and current on a transmission line can be represented by these two differential equations. Okay, by the first order differential equations. So we'll differentiate this equation further. Okay. So we'll differentiate this equation with respect to Vx again. Okay. That time this will become d square V upon dx square, which will be minus of r plus j omega l into di upon dx. Okay. So we'll substitute the value of di by dx in this equation. We'll plug this equation here. That time d square v upon dx square will be minus of r plus j omega l into minus of g plus j omega c into v. So this will become d square v upon dx square is equal to this minus into minus is plus. This will be r plus j omega l into g plus j omega c into v. Okay. So similarly, d square I upon dx square will be the same thing. Okay, r plus j omega l into g plus j omega c into I. So let's write down that as well. So these are the two important equations which we have arrived by analyzing the transmission line step by step. Okay. So since these terms r plus j omega l into g plus j omega c appears in both these equations, okay, we will give it some name. So that name, let us call it as propagation constant. Okay, let's call this value as gamma. Okay, we'll call it gamma square. Okay, I could have named it anything, but since it was named gamma square. Let's follow that rule. Okay, this is gamma square. So we'll see this equation further. So the differential equation will become d square b upon dx square will be gamma square into v, and d square I upon dx square will be gamma square into I. Okay, so these are the two differential equations. So it's just a guess because they named that constant as gamma square because the solution of the equation will become simpler. Okay, every human being will always try for the simplest solution possible. That is the law of universe. So maybe that's the case. So these are the two equations which define the transmission line. So the interpretation of gamma, we'll see it in later videos. For now, the gamma value is root of r plus j omega l into g plus j omega into c. Okay, so both voltage and current are governed by the same differential equation. Okay, as you can see here. And also the solutions for this differential equation can be written as v is equal to b plus e raised to minus gamma x plus e raised to minus b minus into e raised to plus gamma x, and also similarly I will be I plus into e raised to minus gamma x plus I minus into e raised to plus gamma x. Okay, so where these v plus and v minus, I plus and I minus are some constants. Okay, so this should be evaluated using the boundary conditions. So these are the equation of transmission lines. We'll see in detail about what these constants mean and what is this e raised to plus gamma x and what does this e raised to minus gamma x mean in the actual physical sense of the transmission line. So if you have any doubts till now, please use the comment section. In the coming videos, we'll see the actual graphs of this equation, like how sinusoidal signal will be on the transmission line, what is this v minus, etc. Okay, so thanks for watching, guys. Please subscribe to our channel, and also please spread the word that there is a channel like this which is teaching about the electronics and communication, and also we have started a new gate website which is called as gatece.org. So any students who are interested in cracking gate 2017 can visit the website. Okay, thanks, bye.